Good afternoon, everyone. My name is Fomeric, and I'll be presenting our project called Offshore Wind Turbine. Just an overview of our presentation that we are going to give it to you today. I'm going to start with giving you some introduction about our team, abstract, motivation, project flow diagram, design constraint, prototype testing, cost, final prototype, and some accomplishment and future work that we think that will be, can be done on our prototype. This is our team overview. Ramsey was working on microcontroller programming. Hamza was doing the gyroscope implementation. Bart, DC motor. Myself, working on sensor implementation and control system. We work under the supervision of two advisors. We had Dr. Chin from the mechanical engineering department, and Dr. Bass was from the electrical engineering department. All right, and Dr. Sullivan, as we all know, is our coordinator. Now, our system is what? We are building a floating offshore wind turbine. And the technique that we use to stabilize this platform is a technique that we call a gyroscope technique. A gyroscope technique is based on just a spinning mass and a motor. It's very simple, but the concept, we will go through the concept throughout the presentation. Our goal is to try to reach 50% improvement on a setting time to get the system to get back to a stability based on predefined force, attacking force on the turbine. Motivation, why we choose to work on offshore wind turbine. I mean, some people ask me, why you bother yourself trying to go offshore and not just work onshore? One of the first reasons is that most regions, near coast regions are very popular because big city is getting very crowded. So people tend to go near the coast. So having the platform to be offshore, you're actually reducing the transmission line to reach to the customers. You're reducing the transmission line, which means that you're reducing the power loss. You reduce the power loss, that means you're increasing the power production available to the customers. Also, the wind flow is also consistent offshore wind because you have the absence of topographic feature that disrupt the flow of the wind. Other aspect are using offshore wind turbines, the fact that it's also be able to be relocated easily compared to the offshore wind turbine that's actually working in our coast because they're using concrete to build the platform all the way down the bottom. So you use less material, as you can guess, and more efficient also. This is our project overview. It's pretty simple, pretty straightforward. You have the turbine, you have the wind force attacking the turbine, the wind force and the wave disturbance also. So they're attacking the turbine, trying to make the turbine to tilt. So we have tilt sensor to measure the tilt angle, send the signal to the microcontroller based on program that we establish and condition that we predefine. The microcontroller will decide whether to start the gyroscope, which basically are the motor with the spinning mass. Alright, now for our functional design constraint. Our first goal was to build a laboratory scale model for our design. As you can guess, it's very small, but the calculation we did can be implemented, can be easily used to large scale wind turbine. And I will go through some of the calculation down the presentation, why I'm saying that we can easily use that calculation to actually build up a real scale wind turbine. The control system, of course, you have to calculate the required torque to actually counterbalance the force created by the wind the wave disturbance. Process output, damping system, and the optimal placement of the device. Now, functional design constraint. Now we are dealing with renewable energy, so the first thing to think about is being environmental friendly. So our design, by not using so much material and being offshore, there's a lot of, and I forgot to mention, the fact one of the great problems with onshore wind turbine is the disturbance created by the blade. So basically, people are rejecting the installation of wind turbine on the land because the moving of the blade creates some disturbance that actually bothering people at some point. Sometimes it creates trauma, I think, to some of the people that live on the region. So having the system to be offshore, we kind of eliminate that issue because there's nobody living around. Safety, of course, we try to satisfy the federal offshore energy regulations. Manufacturability, we make sure we use a material that won't hurt or be able to be sustainable. Economic, we make sure our design our costing was 500, and we actually make that requirement. Now our approach, very simple. Like I mentioned, we're going to use the gyroscope technique. We have the gyro stabilizer, the tilt sensor, the microcontroller. 3 elements that actually guide the whole system. Now go through the gyro stabilizer. Gyro stabilizer, like I mentioned, is what? It's just a spinning mass and a motor. But when you talk about spinning mass, there's a lot of information that you need in order to actually build an efficient gyroscope. And to model a gyroscope, it's usually called kg, so the I spin times omega spin. I spin is basically called inertia. Inertia is based on the shape of the spinning mass. And you have the omega spin will also drag. That speed is also provided by the motor. So those two values will define actually what is the model of the spinning mass that you need to actually produce the force or torque necessary to balance the system. And below is our second order differential equation. I'm sure everybody's familiar with that. This is the system that we're working on. We have D is the damping force, K, gravity and buoyancy that we calculated previously, and can be provided if you need more information. We have all the calculations. Now, the video, I know I talked about gyroscope, and I think it's very important that we really understand what's going on because we actually ourselves had to go through a lot of readings to actually understand what was happening. So in the video, we're going to explain a little bit what's happening. So think about this as the spinning mass, and this is the shaft, the motor going in. So we have X, Y. Our design is working on 2 degrees of freedom, so we only work on X and Y. But when we have the mass spinning, there's a force created in the Z axis. That force is called precession. It's that force that we're going to be needed to actually balance out the system. The force and direction of the force is depending on the direction of the spinning mass on the top. And it can be switched. We add that because if you switch, if you can use Z and Y, have the motor on the horizontally, they call a horizontal gyroscope. You can use that. But for our case, we use a vertical type gyroscope. Now we use our ankinometer. Ankinometer is just a sensor that measures the angle and output voltage depending on that angle. We received two sensors from a record company with a value of $200. They offer us those 2 sensors, pretty accurate. The characteristic of the sensor from the data sheet was 2.64 millivolt per degree as sensitivity, low power consumption because we use 5 volt. 5 volt is coming from the Arduino board. Offset voltage was 2.469, and measuring angle was from -70 to +70. We met our requirement for the tilt angle because our requirement for a critical angle was 30 degrees. Now the microcontroller, we use Arduino 2560. Clock speed, analog 60 megahertz, analog peak 6 pin. Programming, we use Arduino 1 that uses C++ as a base to actually write the program. Now we couldn't control the motor directly through the Arduino board, so we had because the motor draw a lot of current, and Arduino board is limited to the amount of current that it can withstand. So we had to use a motor shield. The motor shield was mounted on the top of the Arduino board. So the motor was the motor was driven by the motor shield. So the current was going through the motor shield. We were able to control 2 DC motor, direction and speed, and each channel was capable of withstanding 2 amp per channel. Now procedure, after calculating the center of gravity and the buoyancy and get all the required mass to actually have a floating base, we actually move on to understanding what was happening with the tilt sensor. So we get the voltage output resistance tilt angle using the Arduino board, the programming that we wrote before. And then Next day, we try to get the model of the system. To get the model, we get the output of the system based on the tilt angle of 30 degrees. We measure the time required to get the system stable. That's without the gyroscope. And then we obtain the transfer function. From the transfer function, we work ourselves back to get the torque and the speed of the motor required to get the system back to equilibrium. And finally, we get our prototype to be running, as we can see, we will see at the end of the presentation. Now, the video here will show exactly what happened during our preliminary testing. Our team member is going to tilt the platform or the tower to a 30 degree. How we know it's 30 degree, we had a monitor through the computer using Arduino board to make sure that the tilt was actually 30 degree. So the system is actually working without a gyroscope, and we will see how long it will take to actually get back to its position. Now it's important to know that the reason is getting back actually to initial state so fast or not quite falling is because the center of gravity and the buoyancy was calculated very accurately previously. And now this is what we got as a result. As I mentioned, we worked on getting to understand what was happening with the tilt sensor. So the equation on the top left over there is describing how the behavior of the sensor. The slopes correspond to actually the sensitivity of the sensor. You can see that's a little different from the data sheet. It's because the sensor we used were a used sensor, and the company actually told us that they were used, but they were kind of pretty accurate. And the yellow dot corresponds to the positive tilt, the red dot corresponds to a negative tilt. And now this is the response of the graphic interpretation of what we did previously. It took approximately 25 seconds to the tower to get back to a stable state. That's without a gyroscope. And yeah, it's pretty straightforward. Now, like I mentioned, we worked on a lot of calculation. This is just a little piece of the calculation we did. But we thought it was important to actually mention something that we actually performed during the whole year. So we had on top here, we have the model of the system. As I mentioned, we saw before, it was the second order differential equation. The TC corresponds to the torque of the motor necessary to get the system back to equilibrium. The information as A and B was obtained during our preliminary testing result. And once we got that transfer function, we actually had to calculate the force, simulate the force that was attacking the turbine. So basically, we use a speed of wind of 25 miles per hour because our turbine was actually working at 25 miles per hour. I mean, start to actually build a stable power at 25 miles per hour. So basically, if you want to design a system, if you have a region where you think the flow of the wind can be greater, you can just change the value and calculate the force that was going to attack the turbine. So the force was calculated. The force is called the dragon force. There's two forces actually creating once the wind is attacking the turbine. Because there's the dragon force and there's the lift force. But we're not worried about the lift force because the dragon force is the force that actually makes the turbine to tilt, because they're always parallel to the motion of the sensor, of the tower. So we give this information. The C is the dragon coefficient. It's based on the shape of the blade. All those information can be found online also. After all the calculation, we got the speed to be ranged from actually 2,500 to 3,000 RPM, and the torque of 0.15 to 0.314 Newton meter. And finally, that's the motor that we bought with the spinning mass on the top. The motor was 12 to 24 volt, 25 to 3,000 RPM, the torque of 0.35 Newton meter. The spinning mass was a brass. We used the brass because the high density, and because we're limited on the space, we wanted to actually meet the requirement for the mass while not having to go bigger. And the following video, we will see exactly the testing of the turbine. So we took the test in the river down northeast Philadelphia. Our classmate there is taking information from MATLAB actually. So we're acquiring data using a USB cable to actually get the status of the turbine. So one more time, please. Yes. So it's getting the data through the MATLAB. So MATLAB is doing the monitoring at the same time. So MATLAB will be plotting the response of the system right away. Some people might question me, is it no, it's 30 degrees, but I think we already have all set up for an Arduino board to actually know exactly what degree you were tilting in. And that's the result that we got after doing approximately 3 experiments. It took approximately 8 seconds for the system to get back to a stable state. If you remember, previously we had a 25-second for the tower to get back to a stable state. So we had approximately 68% of improvement on the settling time. We actually passed our goal for initially, because initially we wanted to get 50%. So accomplishment, we were able to build a 2-degree of freedom, self-stabilizing offshore wind turbine, get the accurate torque and speed of the motor, while having the system to be very efficient in terms of power production. That's the overall cost of the system, approximately $334. So we saved approximately $156 to College of Engineering. Very good. Even though we are pretty proud of the project, we think we are really satisfied with what we accomplished. We think some work can be done on that project. One thing we think maybe, because the first time ever a project like that is done here at Temple University, maybe the next group can work on 3-degree of freedom, and not using tilt sensor. So maybe they can use the accelerometer. The accelerometer will actually collect what? Tilt angle and the speed in which the tower is falling. Those two information will be implemented at the same time, because it's important to know the speed in which the tower is falling, because maybe you want to start the gyroscope before, because the speed is pretty high. You don't want the gyroscope to get to that tilt angle. Power efficiency, of course, and why not get the estimate cost for large-scale wind turbine. And that takes me to the end of my presentation. If you have any question, before a question, we have a poster presentation after this. So if you want to know more about the project, you're more than welcome to come. It's at 127. We'll go 127. Yes.
Any questions?
I have to ask, why did you do this in a bathtub?
In the
Why
bathtub?
did you do the testing in the bathtub?
Because we wanted to have
I
a
was really concerned about the laptop.
It's actually,
If there's a sinkhole, it's all over.
it's true. We heard that, but we wanted to really understand. Really see how it was working.
From water, right?
Was he the only one who knows how to swim?
Yes, I actually got a water problem. Cannot swim. Yes, Dr. Wong.
So is your actually the gyroscope that's controlling the tilt angle?
Yes.
So you have so how much force does it generate? How much can it control? For example, do you have some information if there is like 10 miles per hour gust of wind? Can you control that? Or?
Yes. Our design was for 25 miles per hour. So we used that speed of wind to actually to calculate the force that was produced on the turbine. So if you want to go up, you have to go through calculation and get the force and get the torque and the speed of the motor necessary to get back to stability. So you cannot just take this for 50 mile, 60 mile, expect the same result. So our design was based on 25 miles per hour for the wind of the speed. Yes.
Where is the center of gravity of that model there?
The center of gravity is pretty low. I'm not sure exactly. It doesn't show here, but the concrete.
What did you put in that reservoir?
Concrete.
What do you have in there?
Concrete.
Concrete.
Did you put some weight in the bottom? Yeah.
Yes, we had to balance out a little bit because initially they were floating pretty well, but once we add the motors, since the motor was just X and Y directions, so we had to compensate a little bit. So we added a little mass. I think it was about approximately 2 pounds that we added the opposite side to actually reach our stable stage before getting into a testing. Yes.
I had a question about the force that you're applying.
Yes.
Like how well does it model the wind? Because that's pretty much, it felt like it was just like a step and then gone. For the wind, right?
Yes.
The wind wouldn't just be just,
Yes, just the force. That's a constant force, right? That's what you're saying.
yeah, so how would you,
So basically, the force is modeled as a sinusoidal force, but we took the average of that force. If you see our MATLAB code, we have as a sinusoidal signal. So basically, it's changing the time.
so you pretty much took, you took what the force of the wind would be and you took the average, what would it be over a certain time,
Yes.
correct?